Imagine a contest so intense, so challenging, it pits the brightest young mathematical minds from over 100 nations against each other. It demands not just answers, but like profound insight, originality, and this really creative proof-based reasoning. This is the International Mathematical Olympiad, the IMO.
It really is the pinnacle for young mathematicians, a true test.
Exactly. And today we're taking a deep dive into something pretty wild. The claim that a large language model, specifically Google's Gemini 2.5 Pro, might now be capable of winning a gold medal at the IMO. So by the end of this, you'll get a clear sense of how this AI actually tackles such a massive challenge, what its aha moments look like, and importantly, where it still kind of struggles.
Yeah, we're basing this on a really fresh research paper just out this July 2025. It details Gemini 2.5 Pro's performance on the brand new IMO 2025 problems. And we'll also touch on some other related stuff, recent announcements from other big players in AI.
Right, so the big question hanging over all this, can an AI truly reason like a human expert? Or is it just, incredibly good at pattern matching and regurgitating things? Let's try and unpack that.
Well, to really grasp why this is such a big deal, you first need to understand why the IMO itself is considered like the ultimate mathematical challenge and why LLMs have historically just fallen short. So the IMO, it's this prestigious annual competition for pre-university math whizzes, started way back in 1959, now has over 100 countries participating. Contestants face 3 incredibly hard problems in a 4.5-hour session. They do this over 2 days, 6 problems total, and each one is graded out of 7 points.
And it's not just about getting the final number right. It's the proof, the elegance, the rigor.
Precisely. That's the key.
And we're talking problems covering algebra, geometry, number theory, combinatorics, really tough stuff. The human element is just so central. These IMO problems, they demand that deep insight, that spark of originality, the ability to connect totally different mathematical ideas. It requires real creative, proof-based reasoning. It's seen as the hallmark of mathematical excellence.
Exactly. And that's precisely why LLMs traditionally have had such a hard time with it. Think about standard benchmarks like GSM-8K or math. These are mostly grade school or high school level problems. LLMs got pretty good at those. They can do it mainly through pattern recognition, pulling stuff from their training data, like a giant lookup table almost.
But the IMO is a whole different beast, miles beyond that complexity. You need multi-step reasoning, abstraction, real innovation. Stuff that feels like how human experts think.
Right, and this is where LLMs used to hit a wall. They struggled to generalize, they'd hallucinate, basically make stuff up or rely on flimsy shortcuts. So the IMO became this perfect test case, this probe, to see if LLMs could actually reason, not just mimic.
There was some progress, though, wasn't there? Things like chain of thought prompting.
Yes, definitely. COTI, chain of thought, that helped. It basically gets the model to show it's working, generating intermediate steps before the final answer. That did improve performance on reasoning tasks.
But still, there was a gap, a big one.
A persistent gap, yeah. Even the best public models just couldn't handle Olympiad-level problems. They'd make logical errors, lack creativity. Their scores weren't even close to human medalists. It highlighted that critical difference between getting a number right and constructing a logically sound argument.
Until now, perhaps. So this new paper, its core finding is this novel method, right? Based on pipeline design and prompt engineering, tailored for Gemini 2.5 Pro. And the headline result, you have to let this sink in. The model solves 5 out of the 6 problems from IMO 2025. 5 out of 6. That just sounds huge.
It is a significant advance, no question. But, whenever you see results like this, the first thing you have to ask is, how do we know it's real? How do we know the model didn't somehow see these problems before? This issue of data contamination is a massive headache in LLM evaluation. Test data sneaking into training data.
Right, they could totally invalidate the results. So how did they address that? Because that seems critical.
They tackled it directly. They exclusively used the problems from the IMO 2025 competition. And these problems were only released days before they ran the evaluation. So it served as a truly pristine testbed, untouched.
Okay, that's reassuring. It means we're likely measuring genuine generalization and reasoning on problems the AI has definitely never encountered before.
Exactly. It gives the results much more weight.
So let's get into the AI's mind then, this multi-step pipeline. How does it actually work? You said it's kind of iterative?
Yeah, it's iterative, and it's fascinatingly similar to how a human might tackle a hard problem. There's an initial attempt, then self-improvement, then verification, checking, correcting, and finally deciding whether to accept or reject the solution.
Almost like a structured thinking process.
Yeah.
So step 1, Initial solution. What happens there?
The model basically takes multiple shots at solving the problem. It's like exploring different paths, hoping one might lead somewhere useful. The prompt it's given really stresses that rigor is paramount. It's not just about the final answer. And it asks the model to be honest about completeness. Even good partial results are valuable.
And all the math has to be in text.
Yep, text. That's the standard typesetting language mathematicians use. It ensures everything is precise, unambiguous, essential for complex proofs.
Okay, makes sense.
But here's a crucial constraint they found. Even a model as powerful as Gemini 2.5 Pro has a maximum thinking budget. It's measured in these things called reasoning tokens, basically units of text it can process. The limit was 32,768 tokens.
32,000.
Okay.
And that's not enough.
Often, no. Not for a typical IMO problem. The paper says the model almost always uses up its thinking budget, just in that first step, trying to get an initial solution down.
Wow. So it hits a computational wall, basically, like AI writer's block, but literal.
Pretty much. And that's where step 2, self-improvement, comes in. It's really clever. They essentially break the problem-solving process. This allows them to inject another budget of 32,768 tokens. So the model gets a second wind. It reviews what it did in step 1 and keeps going, refining its work. And the outputs get noticeably improved.
Okay, so it gets a first draft, hits a limit, then gets more thinking time to refine that draft. What happens next? This verifier.
Right. Steps 3 to 5 involve the verifier. Think of it as an AI peer reviewer, an expert mathematician, but also a really meticulous, picky grader. Its job is to review the proposed solutions step by step, checking for mathematical rigor. But, and this is key, its only job is to find and report issues. It doesn't fix them.
Ah, okay, so it just flags the errors, like a supercritical proofreader. Does it differentiate between types of errors?
Well, yes. It categorizes them. Critical errors are the big ones, logical fallacies, factual mistakes that just break the argument. Then there are justification gaps, where an argument is incomplete, maybe a bit hand-wavy, or assumes something it hasn't proven yet. The verifier notes these down too.
And this is iterative.
Very iterative. The verifier spits out these bug reports. The main model takes those reports and tries to fix its solution. Then it goes back to the verifier. This loop repeats a sufficient number of times.
What if the verifier misses something? Can it make mistakes?
Oh, it absolutely can make mistakes. It's still an AI. But the paper says critical errors are seldom missed, and the system is designed to be quite robust. If an error slips through one round, it might get caught in the next. It's like real peer review. The feedback might not be perfect, but the process encourages the author, the model in this case, to keep improving the clarity and soundness of the argument.
How many times does it need to pass the verifier's check?
A solution is only accepted if it passes the verifier's check 5 times consecutively. It really has to be solid.
Wow, okay. 5 times. That's rigorous. So let's talk about the actual IMO 2025 problems. How did Gemini do on each one? Problem 1, sunny lines.
Combinatorial.
It was a combinatorial geometry problem. For this one, the model was actually given a small hint. Try to solve the problem by induction.
Why the hint?
It seems it was mainly to reduce computational resource usage. Induction is a standard technique, so pointing the AI towards it saved it from exploring perhaps less fruitful, more computationally expensive paths.
Okay. Problem 2, geometry.
Yep, geometry, circles, orthocenters, tangency, classic geometry ingredients. Here, the hint was to use analytic geometry, basically coordinates, and this one turned out to be, quote, the easiest problem in IMO 2025 for AI.
Really? How did it do?
On the very first try, Gemini 2.5 Pro gave an almost correct answer. There were just some small calculation mistakes which the verifier caught later. Pretty smooth sailing on that one.
Nice. Problem 3, Bonza functions. Sound like number theory. Number theory, indeed. This is where the pipeline really flexed its muscles. It sampled 20 different initial solutions and then iteratively improved them using the verifier feedback loop. Eventually, it found a rigorous solution, determining the smallest constant c for these Bonza functions is c4.
Okay, so the iterative process was key there. Problem 4, proper divisors. Also number theory.
Yes, another number theory one. This dealt with infinite sequences and sums of divisors. The model successfully figured out the specific conditions the starting number, A1, of such a sequence must satisfy. Like, it has to be even, divisible by 3, but not divisible by 5. It nailed down those constraints.
Impressive precision.
Yeah.
And problem 5, the inequality game. Game theory.
Game theory, correct. 2 players, Alice and Baza. The AI had to figure out for which values of a parameter, lambda, Alice wins, Baza wins, or it's a draw. And it did. It found the critical threshold for roll is the square root of 2 divided by 2. Above that, Alice wins. Below, Baza wins. Exactly on it, it's a draw.
So that's 5 problems solved. What about the 6th one? Problem 6, tiling a grid.
Yes. Problem 6. This was a combinatorics geometry problem about tiling. And this was the wall. The model only reports the trivial upper bound 4048, which basically means it didn't find any sophisticated solution or insight. It just gave a very basic, obvious limit.
So it failed on that one. Why do you think that was?
It really highlights the current limitations, I think. Highly abstract spatial reasoning, especially in tricky open-ended combinatorics like tiling problems, that seems to still require a kind of creative leap, an intuition that this pipeline approach, even with iteration, couldn't quite generate.
That's really interesting. So even with this incredible performance, there are still frontiers. Okay, stepping back then, what does this all mean? What are the big takeaways here for AI reasoning?
Well, the most striking thing is bridging that gap we talked about. LLMs used to be poor at creative proof-based reasoning. This work strongly suggests that, actually, our current powerful models are capable of solving really difficult math reasoning problems, given the right framework, like this pipeline.
So it pushes back against the idea that they're just glorified parrots. It suggests something more like actual reasoning is happening.
It certainly pushes in that direction. It addresses those concerns about just replicating memorized stuff. And developing these robust reasoning capabilities is absolutely crucial if we want to trust AI in, high-stakes areas. Think scientific discovery or formally verifying software or hardware. We need correctness, not just plausibility.
And it's not just Google, right? You mentioned OpenAI.
Exactly. Around the same time this paper dropped, OpenAI also announced their models achieved gold medal level performance on the IMO 2025.
Wow. So it's a race, or at least rapid parallel progress.
Seems like it. It's clearly a major focus. The researchers on the Gemini paper even suggest that combining different top models like Grok 4, OpenAI's latest, could lead to even stronger math abilities. It's a very hot area right now.
Okay, so to wrap up, we've seen how this sophisticated pipeline, with its iterative refinement and AI verifier, allow Gemini 2.5 Pro to tackle these incredibly hard IMO problems, solving 5 out of 6. It's pushing the boundaries of what we thought LLMs could do in terms of actual reasoning and proof.
Absolutely. It's a remarkable demonstration.
Which leaves us with a pretty provocative thought, doesn't it? If AI can now perform at gold medal level in a competition designed specifically to identify the next generation of human mathematical leaders, well, what does that mean for us? What new kinds of human-AI collaboration in science and problem-solving might this unlock? And maybe even more fundamentally, how might this change the way we ourselves learn and teach complex subjects now that we have this new kind of reasoning engine emerging? Something to think about.